the end of the last video, I said that the easiest way to do this problem would be to distribute the 3 to each piece first. That's certainly one option. I realized, though, after I said that another viable option would be to simply combine the logs inside the brackets into a single log and then bring that 3 up and make it a power. Either of those is perfectly fine. I'm going to go ahead and follow my own advice from the last video and distribute that 3. So we'll have 3 natural log of x minus 3 natural log of x plus 3 minus 3 natural log of x minus 3. And now in each of those terms, I can bring that 3 up and make it an exponent. So it's the natural log of x cubed minus the natural log of x plus 3, the quantity cubed, minus the natural log of x minus 3, that quantity cubed. Now that the coefficient in front of all of my logs is 1, I can consolidate this into a single log of a fraction. The x cubed goes on top. Since that's negative, the x plus 3 cubed goes on bottom. And since that's negative, the x minus 3 cubed also goes on bottom. Now, because everything is taken to the same power, I could, if I wanted to, interpret that as the natural log of x over x plus 3, x minus 3, that entire fraction cubed. Okay? And that's what I would have gotten if I had consolidated here and then brought the 3 up. I'm okay with you either having the entire fraction cubed or the individual pieces. We could simplify a little bit further here, because I can do the multiplication and say that's x squared minus 9 on the bottom. If I had the 3 on each piece, I could have noticed that because this is the same, I can go ahead and do that multiplication in the base. So I could have written this as natural log of x cubed, x squared minus 9 cubed. So a lot of variety in the options for how you can do things. In this case, it was just that one exponent applied to the entire thing. And I'm actually okay with you applying that to the individual pieces on top and bottom, or do you applying it to the entire fraction? Okay, let's try another problem here. Let's say I had the log base 2 of 120 minus the log base 2 of 30. Now, these are just numbers, okay, but 120 isn't a nice power of 2, and neither is 30. So if I wanted to evaluate this as is, I would need a calculator, but if I combine them using my rules of logs, notice what happens. This becomes the log base 2. I'm subtracting logs, whoops. I'm subtracting logs, so I'm subtracting exponents, so that corresponds to division. So this would be 120 divided by 30. Ooh, that's the log base 2 of 4. Now that's nice, because 4 is just a power of 2. So I can evaluate that. If I give it a name, I'm just going to call it x. I can rewrite it in exponential form. The exponent I need when 2 is my base to get 4 as a result is x. Well, 2 squared would be 4, so my exponent is 2. So here's an example where our rules of logs made it a little bit simpler to evaluate something without having to rely on technology. Okay. Couple problems in your book also give you the value of certain logs. So let's just say I had the log base b of capital A was 2. And the log base b of capital C was 5.1. And then let's say I was asked to calculate the log base b of a squared times c. I was asked to evaluate what that was. Well, I can use my rules of logs, okay? Because I can say, hey, that's just multiplication, so I can break that up into a sum of logs. So this would be the log base b of a squared plus the log base b of c. Now I can use my power rule here. So So I would have 2 log base b of A plus the log base b of C. And then I can use the fact that I was given those 2 values. So the log base b of A was 2, so this is just 2 times 2, plus the log base b of C was 5.1, so that's going to equal 9.1. So you'll see a couple of problems like this in the homework where you're given some specific logs. In the homework, they actually give you some decimal approximations for some logs with some actual numbers. I just stuck with variables for this particular example.